I'm going to be talking about the Pythagorean and negative angle identities. All right? First, let me make clear what people mean when they use the term identity. Okay? So, here we go. Equations relate quantities, whereas identities relate functions. Let me repeat that. Equations relate quantities, whereas identities relate functions. Maybe an example will make that more clear what I mean. So suppose we had an expression x plus 1, and that corresponds to some quantity, and I want to make the statement that the quantity that that expression corresponds to is equal to 9. Okay, so this is an equation. These two quantities must be equal. All right, so typically or often what people are interested in is using equations to solve for unknown variable values. In this example, the value of x would be 8, and we can determine that from the equation, right? Okay, so that you're probably familiar with that, examples like that. Now, let me show you an example of an identity. So if you know about fractional exponents, you know that x to the 1/2 is equal to the square root of x. Now, let's think about what I wrote there at the bottom. Okay, what's going on there? Well, that's not really something that you would solve for an unknown value of the variable, is it? Okay, you can't really solve that for, well, you could, and you would see that it can be any value in the domain of the functions on both sides. Okay, but the purpose of that identity is to say, okay, you have this function equal to this expression, x to the 1/2. You have this other function equal to this different expression, the square root of x. And you want to make the statement that both of those functions are really equal. They're really the same function. Okay? There's an example of what you would use an identity for. All right? So now, let me list the identities, the trigonometric identities I'm going to be focusing on now. And then I will discuss further. Now, these identities, surprisingly, maybe, are true for all possible angle measures. Let me repeat that. These angle identities are true for all angles. All right, let me show you now why these angle identities are true. Okay? To understand why these angle identities are true, you must know the coordinate-based definitions of sine, cosine, and tangent. All right, so here we go. I'm going to draw a coordinate plane with a circle centered at the origin. And I will draw it. I'll draw a radius. Okay, and I'll call the angle that corresponds to that radius theta. Okay, and we know that for every radius and coordinate plane as I've drawn, we know that we can find a corresponding right angle as shown. All right, and we furthermore know that if the length of the radius I've drawn is r, okay, and if the legs have lengths x and y, okay, then we can calculate what the sine and cosine are in terms of x, y, and r, okay. Now, I think you would also agree that the Pythagorean theorem is true for that triangle. So therefore, x squared plus y squared equals r squared. Okay, let me now divide both sides by r. X squared over, or excuse me, divide both sides by r squared. X squared over r squared plus y squared over r squared equals 1. Okay, now notice that the last purple equation that I drew is that there's fractions that are equivalent to sine and cosine in there. Okay, the first one is x squared over r squared is equal to cosine squared, and y squared over r squared is equal to sine squared, right? So therefore, I've just proven the first identity. Okay, I can replace in that purple identity, I can make the put in sine and cosine, and I would get the first identity. Okay? So now we understand that the first one comes from the Pythagorean theorem. Okay? Let's now look at the other one. So let me draw the radius that corresponds to negative theta. Okay? And think about how the right triangle that I drew that corresponds to the angle, think about how it's related to the initial right triangle. Well, they both have a hypotenuse with a length of r. They both have legs, corresponding legs that have the same length. Okay? The original point had coordinates x, comma, y. The let's see, maybe we should, for the original triangle, maybe we'll do it, we did that one in blue, so let me draw the coordinate, and maybe this will make it a little bit more clear, but let me draw the original, the coordinates of the original point as x comma y, refer to it as x comma y, and now let me draw the new coordinates of the new point in red. So in terms of the coordinates of the old point, the x value, the x coordinate is going to be the same, but the y, the legs, the lengths of the triangle legs are the same, but the y coordinates are going to differ by -1. So x comma minus y, right? Okay. Now, we know that the sine, the definition of sine of an angle is related to the y-coordinate. So the reason that the second identity is true is because the y-coordinates differ by -1, by a negative sign. Okay, so that's why the sine values on both sides of the second identity differ by a minus sign. Okay? Now, notice that for my 2 points, the blue and red point, notice that the x-coordinates are equal. All right, and also notice that the cosine function is related to the x-coordinate. Okay, so the third identity is true because the x-coordinates are equal for the 2 points that I've drawn in my picture. Okay, and then the last one, well, for the last identity, we know that, or you can see, if you didn't know, that the tangent of an angle, such as theta, is equal to the sine divided by the cosine. So one way to see that the last black identity is true is simply by using the second and third identity, okay? Or you can use the fact that the tangent of an angle is related to the y and x coordinates. It's the ratio, okay? So look, compare the ratios of the blue coordinates and the red coordinates. Can you see that they're going to differ by a negative sign? Right? So therefore, that's why the last identity is true. So I gave you 2 ways to see that the last identity is true. Okay?